as her first chair lecture.
Thank you. Thank you for introduction. It's my great pleasure to give lectures at CRM. Thank you very much. So, I'm from Chiba University in Japan, and my major is discrete integral systems and related topics in cluster algebra and representation theory, or algebraic geometry, and so on. So I'm interested in applications of various mathematics in discrete integral system or some rational maps. So, but today, as the first lecture, I'd like to introduce several topics in several topics of combinatorics appearing in representation theory. So this is my plan. First, I introduce a very basic notions in cluster mutation, in cluster algebra. And after that, I introduce cluster realization of Weyl groups. Then next, I will show two applications of this Weyl group realization. So this is a very rough view around cluster algebra from my point of view. So in the background of cluster algebra, there are two important things. And from algebra, totally positive matrices, and from geometry and Teichmüller theory around punctured surfaces. So also tomorrow I will explain more detail about this. But today's topic with representation theory is based on the relation of cluster algebra with root systems or several representation theory. So also there is various related topics around cluster algebra, like categorization of cluster algebra called cluster category, or quantization of cluster algebra, and so on. Then almost all of them are related to many topics in mathematical physics. And this is why I'm interested in cluster algebra very much recently. And let me explain a little bit about the cluster mutation. So let I be a finite set of integers from 1 and n, and we consider a triple called a seed. So consisting of n by n skew-symmetric integral matrix, it is called an exchange matrix. And this is n tuple of algebraically independent variables called cluster variables or x variables for today. And we have another n tuple of variables called coefficients or y variable. So we use this information to define cluster mutation. So for each element k in this index set I, we define some algebraic transformation from seed to another seed called mutation at k. Then this is a definition of mutation. And actually, this is a definition of mutation for exchange matrix B. And it is again a skew-symmetric matrix. And these are the transformation for x and y variables. And if you are not familiar with cluster algebra, please don't try to memorize this formula now. It doesn't. It isn't very important for now. So actually, this gives a rational transformation for x and y variables. Then today, I only consider the case that B is skew-symmetric, but in general, this mutation is defined for skew-symmetric matrix. So in the skew-symmetric case, there is one-to-one correspondence between skew-symmetric matrix B and a quiver without one loop and two circles. The correspondence is given by this. So ij entry of the matrix B is the number of arrows from I to j in the quiver minus the number of arrows in the opposite direction. So this is the correspondence. So it means that if you two cycles in the quiver, they are canceled by this formula. So this is the basic things. And let's check a very educative example of mutation. So this is the quiver with 4 vertices, namely it is given by 4 by 4 exchange matrix. Then this is x and y variables. So let's consider the mutation at vertex 1. So the previous formula says that first you inverse these arrows related to vertex 1, like this, and next for each pair, such that one arrow is coming to 1 and another is going from 1. For such pairs, we add this arrow to make oriented triangle. So after we did this operation for all pairs related to vertex 1, then we add remaining arrows like this. And this is the resultant quiver. So for x and y variables, there are some rational transformation. And next, let's mutate at vertex 2. And this is a resultant quiver, which is obtained in the following way. So first, we reverse all arrows. In this case, we have 3 arrows related to vertex 2, like this. And so in this case, we have 2 pairs, such that one is coming to 2 and one is outgoing from 2. We have 1, 2 pairs now. So we add 2 arrows to make 2 oriented triangle from 4 to 1. And for this, we add 4 to 3. And we add remaining 2 arrows from 1 to 4 and from 3 to 4. Then we erase 2 circles. So there are no arrows among 1, 4, and 3. So this is the resultant quiver. And for x and y variables, transformation becomes more complicated. And actually, this quiver is called Dinking quiver of D4 type. So if you know the Dinking diagram of D4, that is nothing but this. That is nothing than this one without arrows. So in this way, we define the mutation of seed. So it is easy to check that each mutation is involutive, and that if there is no arrow among I and j vertices in the quiver, namely Bij is 0, then the corresponding mutations are commutative. These are basic property of mutation. Then, by using such operation, from now I introduce a cluster realization of Weyl groups. So let's consider G, finite dimensional semisimple algebra whose rank is S. And this capital S is a rank set. Then from now, I continue to consider the skew symmetric case, namely G has a simply realized Dinking diagram. Then in this case, we define the Dinking quiver for G as follows. So there is I number at the vertices in Dinking diagram. And so by following this number, if J is bigger than I, then we draw an arrow from J to I if they are connected. So next, we fix integer bigger than 1, m, and we prepare m copies of Dinking quiver and assign them on the cylinder. Then by adding several vertices, we define quiver QMG. So it has an M periodicity in the direction of cylinder, and its vertex set is given by Bin, and I is in the rank set S, and N is integer modulo M. So let's see an example. This is a case that G is A type. So this picture shows S is 4. And this is the fixed thinking quiver first. Then we prepare m copies of this on the cylinder. And this rectangle means the fundamental domain on the cylinder. And we add vertical arrows first and diagonal arrows. So this is a definition of QMG in this case. Then you find that there are several oriented circles in this quiver. So W by rank I in S. So the PI is an oriented circle. In this picture, it is a vertical circle. So we have M circles in this picture. Then for each such oriented circle, we introduce a sequence of mutation along this circle. So this is a little bit more general setting introduced by Bucher in 2014 from a little bit different path. So this mutation is given in the following. So for an oriented circle P like this, we define RPB1 first. So B1 denotes the starting point of this mutation sequence. So mu1. So mu1 is for the mutation at vertex V1. Then we continue to mutate mu1, mu2, and so on up to mu p at the end. And this means that we interchange the name of vertices p and p minus 1. And after that, we multiply the inverse of this element from p1 to p minus 2. So we skip the last 2 points to define this sequence. So this curious sequence of mutation has a nice property, as I explain next. So actually, we generalize this definition for circle in the previous quiver. So for circle PI, there are m vertices from B1, B11 to B1m, and we choose one of them, and we start with this vertex and define this sequence mutation in the same way. Then, this mutation sequence satisfies the following theorem. So first, each mutation sequence R preserves the quiver. And next, actually, this mutation sequence doesn't depend on the starting point on a given circle PI. Namely, if n is different from k, and this sequence acts on the seed in the same way, then it doesn't depend on the starting point. So we write Ri for this sequence of mutation, and we call it a cluster R matrix. So the reason we call this the cluster R matrix appears in the third plane. So Ri, I is in the rank set, generate the Weyl group action on the rational functional field generated by X or Y variables, because it doesn't change the quiver, so it is well defined. And namely, so Ri satisfy this Coxeter relation. And so if I and J is equal, then Mij, Mii is 1. It means that Ri is involution. And if I and J are different, depending on the quantity of the product of the Cartan matrix, and we have these things. So actually, today I only deal with the simply laced case. We only have 0 and 1 for this quantity. So m becomes 2. So when m is 2, it means that they are commutative. And m is 3. This is nothing but the famous braid relation or Yang-Baxter relation for R matrix. Then let's how mutation occurs to this group. So this is a case that M period is 4 in this direction, and the quiver, thinking quiver is A3 type. So let's try to mutate in this middle side. So let's, for example, first mutate at 2, and this operator shows the change of quiver. So we come this way, and we exchange the last 2 vertices, and we go back here, and we recover the result. So this means that the sequence of mutation preserves the quiver. But X and Y variables are non-trivially changed. And let's continue, non-trivially changed. So, and this is a thinking diagram. I think many of you already know this diagram. So today I only describe the case A and D and E, and I number the vertices in this way. And the non-trivial action of our matrix on the rational functional field generated by cluster Y variables are written as this. So this is a complicated rational transformation. So when this index I and the index K, and this superscript means the rank, and this N subscript means the lattice coordinate in the direction of cylinder. So if I and K are the same, and it gives this one. And if K and I are connected in linking quiver, and from I to K we have arrow, then it is this one. And the direction is opposite, we have this one. And there is no arrow in linking quiver, it doesn't change. So in this way. And Xi is a polynomial in Y variables like this. Then this is an example of Q3A3. I'm sorry that we don't have Q4 here because the formula is very long. So I want to reduce the length of the formula. So this is a formula. So you see that the action of R to Y variables depends on the linking quiver very much. So in this case, for example, so in linking quiver, 3 and 1, they are not connected by arrow. So in this case, Y1 isn't. So this property is summarized in the following way. So the while group action on Y variables is related to the action of Y group on simply. Actually, if you make a product of all variables on the case circle, and we write Yk for this product, the induced action on this Yk of I is this one. So this is nothing but the multiplicative version of the action of Y group I on the. We can say that by variables. So in this quiver, some group analog form is. And this is a remark for specialist cluster. So actually, I is a free sequence of this quiver Q and K. This is specific sequence in the for given.
Sorry.
Do you hear me?
Can you hear us?
Oh, real. Hello.
Can you hear me now?
Can you hear me now? Can you hear me?
Yes.
Microphone.
Can you try speaking?
So, how long?
Wait a second.
May I mute, please?
All right. Can you try speaking now?
Can anyone hear us now? Yes. Okay. So now you can continue.
Yes.
Yeah.
So
So the mic is here for now.
where is the mic?
Just it's disconfigured the mic right now
Okay.
because the mic there doesn't work anymore.
Oh, okay. So I try to speak
Yeah.
to this laptop. Okay. Okay. So let's continue. So where I stopped. Okay. So okay. By this rational transformation for a pair of vectors, we generalize this to the action on S+1 tuple of same vectors of same size M. So Rj acts on the J's and J plus first vectors like this. And so then this Rj from for J is from 1 to S generate the Weyl group action of A type on the rational function field generated by all variables appearing in these vectors. So namely, this is involution, and if I and J are different more than 1, they are commutative and they satisfy this Lambda relation. So this gives a Weyl group action of A type. Then the good thing for this thing, the reason this action is called geometric R matrix is as follows. So via a limiting procedure called tropicalization, this is the algebra isomorphism from subtraction-free operation of plus and minus to a piecewise linear operation, so minimum and plus. So by sending this on real numbers formally, we get the combinatorial R matrix of the A type, which acts on the tensor product of M of symmetric crystals of SLM type from this geometric R. So this is why the previous rational transformation is called geometric R. So then actually the combinatorial R matrix is given in the following way. So it is M tuple of non-negative integers whose summation is K. This set is named BK. And so in the semi-standard Young tableau, this is a one row tableau with ranks K, and we fill from number from 1 to M in these boxes. Then combinatorial R matrix for this BK is operation from BK times BL to the interchanging, so BL times BK. So this was originally for integer, so it was a piecewise linear map, but it is lifted to the geometric case, like geometric R matrix. So this is why geometric R was studied by many people. And so today I'm interested in the invariance of geometric R. So this was studied by these people, and by introducing the loop analogues of elementary symmetric function, or Schur function, or a skew Schur function, and defined in this rational functional field, so generated by Q's. And actually, by defining these things well, they are shown to belong to the invariant subfield of this CQ. And how to define? Today, I also I only introduced elementary symmetric function. Loop analog of elementary symmetric function. It is defined in this way. So ERK, and R is a index of the in this set, index of the rank, and K K is the index of the rank, and so R is for the loop, and so we define this way, and so for K is 0 and K is not in this region, we define in this way, and if we forget the second index related to this loop part R, and then we get the original elementary symmetric function. Then this is an example. So S is 2 and M is 3 case. So E11 is Q11 plus Q23 plus Q32. And if you forget the second index, we recover the original elementary symmetric function of the lowest degree. And this is E12 and E13 and so on. Then actually we define this function in this way. They are preserved by the Weyl group action. And its proof is interesting and related to integral system. So we define this M by M matrix. At the diagonal, we put element in the ice vector Q, and here we have 1, and this T means a spectral parameter to measure how many times it go around the cylinder. And when geometric R sends Q1, Q2 to Q1 prime to Q and Q2 prime, then the corresponding multiplication of this matrix MQ1 and MQ2 is MQ1 prime times MQ2 prime. So namely, this product is preserved by the action of this R. Then by generalizing this fact, we can say that the multiplication product of MQ1 to MQS plus 1 is invariant of the Weyl group generated by the geometric R matrix.
Can I just ask a question? I'm
Yeah.
going to risk of getting slightly lost. So
Yeah.
to start off with, you talked about the sequences of plus computation.
Yeah.
And then you talked about the geometric R matrix.
Yeah.
I mean,
These
are
two,
the two connected?
yeah, they are related soon.
Okay.
Sorry, I think yeah. So then this loop symmetric elementary symmetric function entries in this matrix actually. So namely, it belongs to the invariant subfield. This is the proof. Then actually, after that, it was shown that the invariant subfield is really generated by this elementary loop analog of elementary symmetric function. And more recently, its polynomial part is also generated by them. So the second claim was proved very recent, and it is very strong result. Then this was the story of geometric R. And so there are related several topics in integral systems. So actually, so the motivation of Kajiwara Yamada studied this geometric R was interest in the generalized Q analog of Parnell equation. Its symmetry is related to the geometric R matrix. And moreover, they studied a rational version of Wiestedt-Schoenstedt-Knuth correspondence too. And moreover, so geometric R are related to the network on the cylinder, and it is related to the study of total positivity. So this was studied by Thomas Lam and Patrick Wiatkowski. And in their setting, the matrix M is related to the measurement on the network they defined. It is very interesting aspect. And based on these things, we can study the generalization of discrete total lattice equation by using this M. So by twisting this M, we get the Lux matrix for the discrete total lattice equation. And the product is, when the product is 2, this is really original discrete total. And we can generalize this to increase the number of products. They are the related topics to integral system. Then today I'd like to introduce the relation to a cluster R. So please recall that we have this quiver for A case, and to relate this to the geometric R, we add white vertices for variables q, like this. And this red square means red rectangle, I shall say, relate to the fundamental domain of the cylinder. We consider y variables. So in the terminology of cluster algebra, this pair is called YC. Then we consider a map phi from the rational functional field generated by cluster y variables to this rational functional field generated by Q, assigned to white vertices, given by this formula. So the yin, for example, if y lives on this vertex, it is given by a ratio of Q on this and this. So if you are interested in y variable on this, this is a ratio of this and this. So via this transformation, we get the following theorem. So for I is 1 to m, we have a geometric R matrix and cluster R matrix. So geometric R and cluster R, and they are compatible. So we have this commutative diagram. And this is the first observation. And actually, it is further applied to get the non-commutative analog of geometric R matrix. So for R matrices, so we have various R matrices here. So combinatorial R was originally obtained from quantum R matrix. And there is also classical R matrix. And we have geometric R matrix. And now we have cluster R matrix. They have a case, they are related. And as I said in introduction, cluster R matrix has natural quantization by using quantum cluster algebra. So we have its quantum lift. And also we can construct this one. But for now, we are not, so we don't know what the meaning in representation theory about these things. We can get something nice, but we want to know this more. This is an open problem. This is a story about geometric R matrix. And as the last topic, I'd like to introduce the application to Q character. So this is a different story related to the representation theory of quantum group. So Q character was introduced by Frenkel and Reshetikhin in 1990s. And when the Q is root of unity, this is a deformation parameter to define quantum group, was studied by Frenkel and Reshetikhin. And basic structure of Q characters are the same in both cases. So when Q is generic or root of unity, in a following sense. Q, UQ gay hat. So gay hat is untwisted affine Lie algebra for affine quantum group with Q to 2m is 1. This is a root of unity case. And we can define a Q character map from the Grothendieck ring of the category of finite representation. In this case, it is some restricted representation. From this to Laurent polynomial ring generated by this variable y. So y has two indices. I belongs to rank set, and AI is non-zero complex number modulo Q to 2m. This is called Q character or Q character map. And Frenkel Reshetikhin, and in the root of unity case, Frenkel and Reshetikhin proved that the image of this character map is this one. So this is a little bit complicated thing. So I is in rank set, and we take intersection of this polynomial polynomial ring. And so in Y, so this A is given by as a Laurent monomial, Laurent monomial in Y. So essentially, so this is A is Y. Then this is the example of case A2 case. I think it is not easy to understand this, so this gives some example. So the representation of quantum groups is parameterized by weight and non-zero integer, non-zero complex number A. So in this case, we put fundamental weight omega 1 here. So its image is given by this Laurent polynomial in Y. And actually, this is written in two ways, like this and this. And this expression shows that this belongs to this Laurent polynomial ring in Y for I is 1 because of this expression. And in this expression, we see that it belongs to the case I is 2. So in this way, this expression belongs really an intersection of two of these things. So in this way, so they show this theorem. Then we are interested in if we can describe this image by using the while loop action. This is our problem. And for this, we have to stratify the Laurent polynomial ring Y in some finite things in the following way. So we fix a complex number A in modulo Q to 2 and define a subalgebra of YA in this way. So please note that this is finitely generated. So I belongs to S as before, and N is now finite. So N is modulo M. And here because we fixed A. And here we have AQ to N plus DI. And the DI is some integer given by I. So then we can now reduce the Laurent polynomial ring Y into some finite thing by fixing A. We are interested in the intersection of image of Q character map and this YA. Then from now we relate these capital Y variables to the variables related to the quiver QMG. And the vertex set of QMG is this, so they are the same. They have the same index set. Then we let phi A be the map from this YA to the rational functional field generated by capital Y. So this capital Y is almost the same as this one, but to adjust the lattice related to this quiver, we little bit change the notation, but essentially they are the same. And so let beta be the embedding of the rational functional field generated by cluster Y variables to this rational functional field generated by capital Y by sending Y variables to the inverse of A. So A was the Laurent monomial in this capital Y. So this is some embedding of Y variables in this rational functional ring. So this is bigger than this one. Then we can show that the image of this phi I of this thing, what we are interested in, is written in this way, in the same way as before. Here, GI is now this one. So we have cluster Y variables here, but we have some additional things comes from this capital Y. So, but in this way, we can reduce the complicated thing into a simpler thing. We are interested in what is the action, while group action on this rational functional field. And we define this action first. So if I and j are equal, then there is some non-trivial thing, but otherwise it is trivial fact. And here y bar is again a polynomial in cluster y variables, but it is decreasing. For the first time in the cluster R matrix, it was increasing, but the direction is now opposite. But it doesn't matter actually. And we have the following theorem. For element I in the rank set, we have this diagonal commutative. So we have action Ri, which is we just define here. And we have cluster R matrix action on Y variables. And here, R bar is almost the same as the previous one, Ri, but this R bar is defined in the same way, but for quiver minus QMG. So this minus means the same quiver, but the direction of all arrows are opposite. So this is the reason we have a decreasing sequence now. So essentially, R and R bar both generate the while group action on the same rational functional field. So we now take this one. But it is non-trivial that if this small I, Ri, generates a while group action on this rational functional field, this is non-trivial question. And actually, it is true. So in this way, we can extend the while group action originally defined on cluster setting to this a little bit bigger one. Then this is what we have defined. And we have the following theorem related to the Q character. So we are interested in this, this set. And actually, we can show that via this map, it is in the invariant subfield of Cy. So it is in invariant subfield, and especially each Zi. So Zi is given by this one. So is included in the invariant subfield of Ri. So namely, the intersection of this Zi is naturally included in this subfield. So then more precisely, we can show that the invariant subfield of small Ri is generated by these things. So it is the same as the generator of these things. So something nice occur to this case. So we can now show that this is equal if you take this one. So namely, the intersection of this thing is this invariant subfield of while group action. Then the question is, actually this set is a Laurent polynomial ring in Y. So it is non-trivial question that if this intersection is equal to this one, this is non-trivial question, and we are now interested in this one. So it is very closely related to the theorem I explained for geometric R matrix. I'd like to remark a few things. Today, I only explained about the simply raised case, but there is a story about a non-simply raised case too. And in such a case, the invariant subfield of action of while group has a little bit different structure. And because the quiver QMG is a little bit different. So non-simply raised case, QMG has this kind of thing. So this is an example of B3 case. So the Dinkin diagram of B3 only has 3 vertices, but we have to divide somehow by using the opposite. So unfolding operation to get this quiver. So because of this, this invariant subfield has a little different structure. Moreover, the realization of Weyl group for non-simply left case has another, there is another type. So if we are allowed to have skew symmetric exchange matrix of cluster algebra, we can have this quiver. Actually, this 2 means this vertex has weight 2. So it's a kind of generalization of quiver. If we use this kind of quiver, we have another realization of Weyl group. And actually, this quiver is applied to a different thing in mathematics. So this is for Q character, and this is for another thing. Moreover, today, I only study the case that M is finite, so it has a periodicity along cylinder, but we can take the infinite version, so semi-infinite or full-set infinite, or we can take such cases. Then in such a case, this quiver was introduced by Hernandez and Grach to study cluster structure of Q characters from a different point of view based on categorification. So this quiver is closely related to the structure of Q character. So there are several branches. And in closing, I'd like to mention the other topics related to this quiver. So when M is 2 and the G is affine A-type, then this quiver realizes the symmetry of discrete Panrove equation. Recently, this is studied by these people. So as you know, so discrete Panrove equation or its generalization has always have a Weyl group symmetry, and this is realized by using this quiver. And another topic is that when the period M is a Coxeter number, H of the real algebra G, then this quiver QHG gives the cluster structure of the higher Tachina space of one's punctual disk. So I will talk about this thing in my second and third lecture, where the Weyl group generalization in this quiver is related to the geometric Weyl group action around the puncture. So it has a geometry, it is interpreted in the geometrical setting too. So there are several interesting topics around this quiver QMG and Weyl group action. So I don't talk about the Panrove equation anymore, but about geometry, I will add several things tomorrow and on Wednesday. So this is the end of my talk. Thank you very much for attention.
Yeah, I guess I don't know if the mic is working. So is there a simple relation between your geometric R matrix and the usual braided R matrix?
Braided means the generator of braid group.
As far as I understood, you can take a limit when Q goes to 0 to get the combinatorial R matrix, or an ultra discrete limit from the geometric R matrix.
Yes.
So it's both.
I mean this right.
Yeah. So both from the quantum R matrix, is there a simple relation to the?
From here to here, as far as I know, there is no direct relation. Yeah. So yeah, it's already so they are related to this combinatorial one. So it is very deterministic limit. of this quantum one. And this geometric R is deterministic from the beginning. So
Maybe to link with the first talk of this morning, we discussed about the K matrix. You have the geometric K matrix.
oh, yeah, I'm sorry, I missed.
Sorry.
Yeah.
You are
But I
repeating.
know geometric K matrix.
It
Yes,
exists?
yes.
Okay.
Is there a question
The question is, there exists a geometric K matrix?
for this geometric R?
Yes.
For this one, I'm sorry, I don't know about this one. So it should be interesting question. Yeah.
Because normally it's linked more to the B,
Yeah.
the B type Weyl group. So
Yeah.
we
Yes.
expect
Yes.
a K matrix at this point.
Yes. Is there combinatorial K matrix?
Yes.
Oh, really? Oh, that's good. So it's natural to have geometry. Maybe somebody already studied that. I don't know.
What is the parameter epsilon? I understand Q is what epsilon.
In this
Yes, in this.
Q,
Q, I understand.
yeah, epsilon.
Yes.
Epsilon is a deformation parameter to define quantum cluster algebra. It is non-commutative algebra, and usually, so it was introduced by Fock and Goncharo, but they used Q. But I've tried to avoid the confusion between Q and
But it's
another.
the same idea, more or less.
Yeah, same idea. To deform the algebra to quantum. Very similar.
So it's no more deterministic.
Yes.
The constant cluster R matrix and the constant R matrix are not direct, right?
Yeah, that's a very nice question, but I don't know for now. So actually, it is based on, so in general, it comes from universal R matrix, about quantum R matrix. By setting some representation, we get some finite one. But in this case, the situation is very different. I have no idea about it.
There's no other questions. Let's thank